Welcome to today's session. In this video, we will explore a fascinating problem titled Distance Between Bus Stops. This challenge requires us to calculate the shortest distance between two bus stops on a circular route. It's a great exercise to strengthen your understanding of array manipulation and problem-solving skills. Let's dive in. In this problem, we are working with a circular bus route that contains n stops, numbered from 0 to n1. The circular nature of the route means that after the last stop, the bus loops back to the first stop. We are given an array called distance that holds the distances between consecutive bus stops. For example, distance, I, represents the distance from stop I to stop, I plus 1, %n, where the modulo ensures the circularity of the route. Additionally, we are provided with three inputs, the distance array, a start stop, and a destination stop. The goal of the problem is to compute the shortest distance between the start and destination stops along this circular route. The output of the problem is a single integer representing the shortest distance between the two specified stops. Let's look at an example to clarify the input-output relationship. Suppose the input is distance equals 1, 2, 3, 4, start equals 0, and destination equals 1. The shortest path is straightforward in this case, as the bus travels directly from stop 0 to stop 1, which has a distance of 1. Therefore, the output is 1. This example demonstrates a simple case where the shortest path does not require evaluating alternative routes. Now consider a slightly more complex example with the same distance equals 1, 2, 3, 4, but this time start equals 0 and destination equals 2. Here, the distance from stop 0 to stop 1 is 1, and the distance from stop 1 to stop 2 is 2. Adding these together, the total distance along this path is 1 plus 2 equals 3. Alternatively, if we consider the reverse direction, traveling from stop 2 back to stop 0, the distance would be 4 plus 3 equals 7. Since the shortest path is the forward direction with a total distance of 3, that is the output. In another example, let's take distance equals 1, 2, 3, 4, start equals 0, and destination equals 3. The distances along the forward path are as follows. From stop 0 to stop 1, the distance is 1, from stop 1 to stop 2, the distance is 2, and from stop 2 to stop 3, the distance is 3. Adding these together gives a total distance of 1 plus 2 plus 3 equals 6. In the reverse direction, traveling from stop 3 back to stop 0, the distance would be just 4. Therefore, the shortest distance in this case is 4, which is the output. When solving this problem, there are some important edge cases to consider. For instance, the smallest valid input occurs when n equals 2, such as distance equals 1, 1, with start equals 0 and destination equals 1. For large inputs, where n and the values in the distance array reach their maximum limits of 10, 0, 0, 0, the solution must handle these efficiently. Circular paths also introduce interesting scenarios, such as when the shortest path involves traveling in the reverse direction of the route. Additionally, it's important to test cases where the stops are very close, like consecutive stops, as well as cases where the stops are far apart, requiring a comparison of both forward and reverse distances to find the shortest route. These considerations ensure the solution works across all possible inputs. To start, let's summarize the problem. We need to calculate the shortest distance between two bus stops on a circular route. The distances between consecutive stops are given in an array, where each element represents the distance between one stop and the next. Since the route is circular, the last stop is connected back to the first stop. This circular nature creates two possible paths between any two stops, one in the clockwise direction and the other in the counterclockwise direction. To determine the shortest path, we can follow two key observations. First, the clockwise distance can be calculated by summing the distances as we move forward through the array from the start stop to the destination. Second, the counterclockwise distance can be derived by subtracting the clockwise distance from the total distance of the route. This insight allows us to avoid redundant calculations, making the solution more efficient. Now, let's consider the brute force approach, which is the most straightforward way to solve this problem. The idea here is to calculate both the clockwise and counterclockwise distances explicitly, and then simply return the smaller of the two. To achieve this, we sum the distances in the clockwise direction by iterating through the array from the start stop to the destination, taking care to handle the circular wraparound. Similarly, we calculate the counterclockwise distance by summing the distances in the opposite direction. In terms of complexity, this approach has a time complexity of O(n), as we may need to traverse the array twice, and a space complexity of O(1). While this method is simple to implement, it involves redundant calculations for the total distance, which can be avoided with a more optimized approach. Now let's focus on the optimized approach, which eliminates redundancy and improves efficiency. The key idea here is to leverage the total distance of the circular route, which can be pre-computed in a single pass. Once we have the total distance, we can calculate the clockwise distance by summing the distances from the start-stop to the destination directly. Then, instead of explicitly summing the counterclockwise distances, we can derive it in constant time by subtracting the clockwise distance from the total distance. Finally, we return the smaller of the two distances. This approach has a time complexity of O(n), as we only make a single pass to compute the total distance and another traversal for the clockwise distance. The space complexity remains O(1), as no additional data structures are required. While slightly more involved than the brute force method, this approach is much more efficient and avoids redundant calculations. Another potential solution is to use a prefix sum approach for calculating distances. The intuition here is to pre-compute cumulative sums of the distances in a prefix sum array, which can then be used to efficiently query distances between any two stops. To implement this, we first construct a prefix sum array where each element represents the total distance from the first stop up to that stop. Using this array, the clockwise distance can be determined by subtracting the prefix value at the start stop from the value at the destination stop. The counterclockwise distance can still be derived as the total distance minus the clockwise distance. This method has a time complexity of O(n) for constructing the prefix sum array, with O(1) query time for each distance calculation. However, it requires additional memory to store the prefix sum array, making it less space efficient than the optimized approach. This method is particularly useful if we need to handle multiple distance queries for the same route. After evaluating the different approaches, the optimized approach emerges as the best choice for this problem. It strikes the right balance between simplicity and efficiency, avoiding the redundant calculations of the brute force method and the additional memory overhead of the prefix sum approach. By leveraging the total distance of the circular route, we simplify the calculation of the counterclockwise distance, making the solution both time and space efficient. This is especially suitable for scenarios where we only need to calculate the distance once. The key takeaway is recognizing the circular nature of the route and using it to streamline our calculations. While alternative methods have their advantages in specific use cases, the optimized approach is the most practical and efficient for the given problem. In this problem, we are tasked with finding the shortest distance between two bus stops on a circular route. The route is represented by an array called distance, where each element specifies the distance between consecutive stops. Since the route is circular, the last stop connects back to the first stop, which is why we use the modulus operator, i+1%n to handle the wraparound. To solve this, we can calculate the distance in two ways: the clockwise route, where we sum the distances from the start stop to the destination stop, and the counterclockwise route, which sums the distances in the opposite direction. Our goal is to compute both distances and return the smaller one. To simplify calculations, we start by computing the total distance of the entire route, as it will help us determine the counterclockwise distance more efficiently later on. To calculate the clockwise distance, we initialize a variable, clockwise_distance, to 0. Starting at the start stop, we iterate through the stops until we reach the destination, summing up the distances along the way. The modulus operator, i+1%n, ensures that the traversal wraps around correctly when we reach the end of the array. For the counterclockwise distance, instead of explicitly iterating in the reverse direction, we can use a clever optimization. By subtracting the clockwise distance from the total distance of the route, we get the counterclockwise distance directly. This avoids redundant calculations and improves the algorithm's efficiency. Finally, we simply compare the two distances, clockwise_distance and counterclockwise_distance, and return the smaller value. This ensures that we always find the shortest path between the two stops. What makes this algorithm efficient are a few key insights. First, the use of i+1%n allows us to handle the circular nature of the route seamlessly, ensuring that the traversal wraps around correctly. Second, pre-computing the total distance of the route eliminates the need for an explicit reverse traversal, which not only simplifies the logic but also improves performance. Additionally, the algorithm handles edge cases gracefully. For instance, if the start and destination stops are the same, the distance is naturally zero since no travel is needed. Similarly, it works well with small arrays, including single-element or two-element inputs, due to the modular arithmetic. In terms of data structures, the input distance array is sufficient for storing the route information, while a few variables like total_distance, clockwise_distance, and counterclockwise_distance are used for intermediate calculations, keeping the space usage minimal. Analyzing the algorithm's complexity, the time complexity is O(n), where n is the number of bus stops. This is because we traverse the distance array once to compute the total distance, and then perform a partial traversal, which involves at most n elements, to calculate the clockwise distance. The space complexity is O(1), since we do not use any additional data structures beyond a few variables. Let's walk through an example to better understand the process. Suppose the input is distance equals 1, 2, 3, 4, start equals 0, and destination equals 2. First, compute the total distance of the route by summing all elements in the array. 1 plus 2 plus 3 plus 4 equals 10. Next, calculate the clockwise distance. Starting at index 0, add distance 0 equals 1, then distance 1 equals 2, and stop at index 2. This gives a clockwise_distance of 1 plus 2 equals 3. For the counterclockwise distance, subtract the clockwise distance from the total distance. 10 3 equals 7. Finally, return the smaller of the two distances, which is min 3, 7 equals 3. This approach is both efficient and robust, handling edge cases such as when the start and destination indices are the same, routes with only one stop, and varying distance values without any issues. By leveraging modular arithmetic and pre-computing the total distance, we achieve a clean and optimized solution. This makes the algorithm suitable for a wide range of inputs and ensures that we always find the shortest path in minimal time. This solution calculates the shortest distance between two bus stops on a circular route. The function distance between bus stops receives three inputs: distance, a list where each element represents the distance between consecutive stops; start, the index of the starting stop; and destination, the index of the ending stop. First, the code ensures start is less than destination. This simplifies the computation by allowing us to directly calculate the clockwise distance using slicing. If start is greater than destination, their values are swapped. Next, the clockwise distance is calculated by summing the distances between start and destination using sum, distance, start to destination. This represents the direct route in the clockwise direction. To find the counterclockwise distance, the code first calculates the total distance of the entire circular route using sum, distance. The counterclockwise distance is then derived by subtracting the clockwise distance from the total distance, as the two distances together cover the entire circular route. Finally, the shorter of the two distances is returned using the min function. This ensures that the function always outputs the shortest path between the two bus stops, regardless of the direction. This implementation is efficient, with a time complexity of O(n), where n is the number of stops, as it involves summing subsets of the distance array. Edge cases, such as when start equals destination, are handled naturally, since the sum in both directions would be 0, resulting in the correct output. Here, we begin by defining a method called distance between bus stops that calculates the shortest distance between two bus stops. The method accepts three parameters: an integer array distance representing distances between consecutive stops, and two integers, start and destination, indicating the indices of the starting and destination stops. To simplify the calculation, we first ensure that start is always less than destination. If it's not, we swap their values using a temporary variable. Next, we calculate the clockwise distance by iterating from the start index to the destination index in the array, summing up the distances in that range. We then calculate the total distance around the entire bus route by summing all the elements in the distance array. This total distance will help us compute the counterclockwise distance, which is obtained by subtracting the clockwise distance from the total distance. Finally, we determine the shortest path by taking the minimum of the clockwise and counterclockwise distances, and we return this value as the result. With the closing brace, we complete the implementation of the distance between bus stops method. This approach ensures an efficient solution by leveraging simple arithmetic and iteration. The algorithm effectively accounts for both possible routes, clockwise and counterclockwise, before determining the shorter one, making it robust and easy to understand for this problem. The problem involves a circular bus route represented by an array called distance, where each element in the array specifies the distance between two consecutive bus stops. Given two bus stops, start and destination, our goal is to determine the shortest distance between these stops, considering both clockwise and counterclockwise directions. For the first example, the input specifies distance equals 1, 2, 3, 4, start equals 0, and destination equals 1. Since start is less than destination, there's no need to swap their values. To calculate the clockwise distance, we sum up the values in the distance array from index start to destination. Here, the subarray is distance, 0:1, which equals 1. Summing this gives us a clockwise distance of 1. Next, we calculate the counterclockwise distance by subtracting the clockwise distance from the total sum of the distance array. We'll continue analyzing this calculation shortly. The total distance for the circular route is calculated by summing all elements in the distance array, 1 plus 2 plus 3 plus 4 equals 10. To find the counterclockwise distance, we subtract the clockwise distance from this total. Here, counterclockwise underscore distance equals total underscore distance, clockwise underscore distance equals 10, 1 equals 9. Finally, the shorter of the two distances is selected as the result. In this case, min, clockwise underscore distance, counterclockwise underscore distance, equals min, 1, 9, equals 1. Therefore, the output is 1. For the second example, the input specifies distance equals 1, 2, 3, 4, start equals 0, and destination equals 3. Again, since start is less than destination, no swapping is needed. To calculate the clockwise distance, we sum the subarray from index start to destination, which is distance, 0:3, or 1, 2, 3. Summing the elements in the subarray 1, 2, 3 results in a clockwise distance of 1 plus 2 plus 3 equals 6. Next, we calculate the counterclockwise distance using the total distance of the array, which remains 1 plus 2 plus 3 plus 4 equals 10. By subtracting the clockwise distance, we get counterclockwise underscore distance equals total underscore distance, clockwise underscore distance equals 10, 6 equals 4. To determine the shortest path, we take the minimum of the two distances, min, clockwise underscore distance, counterclockwise underscore distance, equals min, 6, 4, equals 4. Hence, the output is 4. For the third example, the input specifies distance equals 7, 10, 1, 12, 11, 14, 5, 2, start equals 7, and destination equals 2. This time, we notice that start is greater than destination. To simplify the calculation, we swap their values. After swapping, start becomes 2 and destination becomes 7. The clockwise distance is then calculated by summing the elements of the subarray distance, 2:7, which is 1, 12, 11, 14, 5. Adding these values gives 1 plus 12 plus 11 plus 14 plus 5 equals 43, so the clockwise distance is 43. The total distance of the array is calculated as 7 plus 10 plus 1 plus 12 plus 11 plus 14 plus 5 plus 2 equals 62. To find the counterclockwise distance, we subtract the clockwise distance from the total. Counterclockwise underscore distance equals total underscore distance, clockwise underscore distance equals 62, 43 equals 19. The shorter of the two distances is selected as the result, min, clockwise underscore distance, counterclockwise underscore distance, equals min, 43, 19, equals 19. Thus, the output is 19. This problem demonstrates that the shortest distance between two bus stops on a circular route can be calculated by considering both clockwise and counterclockwise directions. The clockwise distance is determined by summing a specific subarray of distance, while the counterclockwise distance is derived by subtracting the clockwise distance from the total sum of the array. Additionally, swapping start and destination when start is greater ensures consistent calculations for the clockwise direction. Finally, the solution always selects the shorter of the two distances, guaranteeing the shortest path is returned. This approach is efficient, leveraging basic arithmetic operations to solve the problem accurately. To determine the time complexity of this function, we begin by analyzing each operation independently. First, ensuring that the start index is less than the destination involves a simple swap operation. This is a constant time operation, O1, because it doesn't depend on the size of the input. Next, we calculate the clockwise underscore distance. This involves slicing the distance list to extract elements between start and destination. Slicing is proportional to the number of elements in the slice, which we'll call k. Summing this sliced subarray also takes k time, as it requires iterating through those k elements. Then, for the total underscore distance, we compute the sum of the entire distance list. Because this summation iterates through all n elements in the list, it requires n time. Finally, computing the counterclockwise underscore distance involves a subtraction operation, which is constant time, O1. The last step involves returning the minimum of the clockwise underscore distance and the counterclockwise underscore distance. Comparing two integers is a constant time operation, O1. Now, when we evaluate the overall time complexity, the slicing and summing operations dominate the runtime. The slicing step takes k, while the total summation of the list takes n. Since k is always less than or equal to n, the summation step, n, is the largest contributing factor. As a result, the overall time complexity of the algorithm is n. This reflects the fact that summing the entire list inherently requires traversing all its elements, regardless of the slicing step. Now let's analyze the space complexity of this algorithm. The algorithm does not create any additional data structures that grow with the input size, which means auxiliary space usage is minimal. For instance, the slicing operation distance, start to destination, does not allocate new memory to hold the slice, it simply references the relevant portion of the original list. Similarly, the summation and subtraction operations return scalar values and do not require extra storage. The input storage, which includes the distance list and the start and destination indices, is part of the input itself and not additional memory allocated by the algorithm. Therefore, the overall space complexity of the solution is constant, or O1, as the algorithm only uses a fixed amount of space regardless of the input size. To better understand the efficiency of this approach, let's compare it to a brute force or naive solution. The naive method would calculate the clockwise underscore distance by iterating through the relevant elements of the distance list in one pass. Then, it would calculate the counterclockwise underscore distance with a second pass, summing the remaining elements. This would involve two separate loops over the list, resulting in a time complexity of n plus n, which simplifies to n. However, the space complexity would still be O1, because no additional data structures are created. The optimized approach improves on this by computing the counterclockwise underscore distance using the total sum of the list, avoiding the need for a second full traversal. This reduces redundant computations while maintaining the same asymptotic time complexity of n and space complexity of O1. Finally, let's consider the best, average, and worst-case scenarios for this algorithm. Regardless of the input values, the summation of the entire distance list to compute total underscore distance always requires one full traversal. Therefore, the best case time complexity is n. Similarly, the average case involves summing the list and calculating the clockwise underscore distance, which also results in n. In the worst case, if the start and destination indices are far apart, the slicing operation might include nearly the entire list. However, since the summation of the entire list is always performed, the dominant operation still gives a time complexity of n. To mathematically justify this, the function performs operations proportional to the size of the input, n, making the runtime linear. The space complexity remains O1, as no additional memory scales with the input size, ensuring the algorithm is efficient in terms of both time and space. When working with this problem, there are several common mistakes to watch out for. First, many people forget that the bus route is circular, which means the indices wrap around. For example, the distance from the last stop back to the first stop needs to be included, and failing to account for this leads to incorrect results. Another mistake involves summing distances incorrectly. Remember, this problem requires you to consider both the forward and backward paths, and you need to compare the two to determine the shortest distance. Additionally, edge cases like when the start and destination are the same, where the distance is naturally zero, or when there's only one segment in the array, must be handled explicitly. Lastly, avoid using nested loops to calculate distances. While it might seem intuitive, it results in n squared time complexity, which is inefficient. Instead, aim for an O(n) approach by leveraging prefix sums or direct summation. Now let's talk about modular arithmetic and its importance in this problem. Since we're working with a circular route, modular arithmetic plays a key role. Missteps in calculations like I+1% or I1+n% can lead to index out-of-bounds errors, so it's critical to validate your operations carefully. From an interview perspective, this problem highlights your ability to compare paths and optimize calculations in a circular structure. Make sure to emphasize your understanding of modular arithmetic and the efficiency of an O(n) solution. Discussing trade-offs is also important. For instance, iterating through the array twice is still linear and avoids redundant calculations. This type of problem also aligns with patterns like circular data structures, pathfinding, and modular arithmetic. Interviewers might extend it to weighted graphs or dynamic programming challenges, so understanding these connections can help you stand out. Additionally, proactively addressing edge cases demonstrates thoroughness and can leave a positive impression. This problem is part of a broader category of challenges involving circular structures, and understanding related problems can deepen your insights. For instance, LeetCode 1184, the problem we're solving, directly focuses on calculating distances in a circular route. LeetCode 918, Maximum Sum Circular Subarray, is another example that involves circular arrays and modular arithmetic, emphasizing the need to think in terms of wrapping indices. Similarly, LeetCode 1243, Circular Array Loop, deals with cycles and movement within circular arrays, showcasing the importance of handling circular structures efficiently. Lastly, while LeetCode 1465, Maximum Area of a Cake after horizontal and vertical cuts, doesn't involve circular routes, it shares the theme of optimizing distances or paths, which is a closely related concept. Familiarizing yourself with these problems can help you recognize patterns and improve your problem-solving skills across similar challenges. To wrap up, let's discuss some alternative approaches and their trade-offs. One efficient method is the prefix sum approach, where you calculate cumulative distances and use these to compute both the forward and backward distances. This ensures an O(n) complexity and improves efficiency, though it comes with a slight trade-off of using extra memory if you store the prefix sums. Another option is the single-pass summation technique, where you iterate through the array once, summing distances in the forward direction, and then subtract this from the total route length to determine the backward distance. While this avoids additional memory usage, it requires careful handling of modular arithmetic to ensure accuracy. Lastly, there's the brute force method, which uses nested loops to calculate and compare distances for each path. While straightforward and easy to implement, its O(n) squared complexity makes it impractical for larger inputs. Understanding these approaches and their trade-offs not only helps you solve this problem efficiently but also prepares you for variations in other scenarios. Great job! We've successfully tackled the distance between bus stops problem. Remember to practice circular traversal techniques for problems like this. If you found this helpful, please like, subscribe, and share with fellow coders. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!